In this video, we will look at Isovist analysis. Isovist analysis is part of a larger field of study known as visibility analysis, focusing on the visibility of entities within an environment. Isovist analysis offers a way of describing space relative to vantage points. It can lead to a more in-depth understanding of the underlying properties of space. It can also be applied in areas such as the privacy and defensibility of space. An isovist is a space visible from a specific vantage point in the environment. In some contexts, this is referred to as a viewshed. Every point in space has an associated isovist. As a person moves through space, the isovist will change continuously. Isovists can be 3D or 2D. In 3D, an isovist describes a volume. In 2D, it describes a planar area. 2D isovists can be in the plan or in section. In urban applications, people will usually be moving around on the ground plane. As such, Isovist analysis is usually performed in 2D, on the ground plane. The topography is usually not taken into account. When calculating the isovist of space, certain lines of sight may be very long or even infinite. Isovist analysis is usually performed with a maximum radius applied to each origin point. Any lines of sight that are longer than this maximum radius are then shortened. In the diagram, the dotted circle represents the maximum radius of the isovist. The 4 red circles indicate where the lines of sight have been shortened. An isovist analysis focuses on the shapes of the isovists. For non-convex environments, different vantage points may have isovists that differ. In the example, the isovists for 2 points are shown in an L-shaped space. Various metrics have been developed that quantify key features of the size and shape of the isovist. Next, we will look at some of the most commonly used metrics. Distance metrics are based on distances from the origin point to points on the isovist boundary. The 3 distance-based metrics are minimum distance, average distance, and maximum distance. The area metric calculates the area of the isovist. The area can be normalized by dividing it by the maximum area, which is the area of a circle with the maximum radius. Values will then all be in the range between 0 and 1. The perimeter metric calculates the length or the boundary of the isovist. In general, isovists with high perimeter values are more complex. The perimeter can be normalized by dividing it by the perimeter of a circle with the maximum radius. Note that in this case, the values can be greater than 1. This is because, for complex isovists, the actual perimeter can be larger than the circle perimeter. The example shown could be such a case. The circularity metric measures the roundness of a space. Isovists with high circularity are closer to a round shape. Circularity is calculated by dividing the square of the perimeter by the area. The compactness metric measures the compactness of a space. For example, a long thin space is less compact than a short fat space with the same area. The compactness ratio is calculated by dividing the average distance by the maximum distance. Values will be in the range between 0 and 1. Finally, the cluster ratio is an alternative measure of compactness. For calculating the cluster ratio, 2 idealized circles are calculated. One circle has the same area as the isovist. The other circle has the same perimeter as the isovist. The cluster ratio is the radius of the first circle to the second circle. Values will be in the range between 0 and 1. Calculating a metric for all points in space creates an isovist field. For each point in the grid, an isovist is generated and analyzed using one of the metrics. Color is then assigned to the point, based on the chosen metric. If a false color scale is used, Blue colors indicate the low values and red colors indicate high values. In the following slides, we will show the false color Isovist field for each of the metrics described before. Minimum distance Isovist analysis. Average distance Isovist analysis. Maximum distance Isovist analysis. Area Isovist analysis. This calculates the area of the Isovist. Perimeter Isovist analysis. This calculates the area of the perimeter. Circularity Isovist analysis. This calculates the square of the perimeter divided by the area. Compactness Isovist analysis. This calculates the average distance divided by the maximum distance. Cluster Isovist analysis. This calculates the ratio of two idealized circles. The Isovist fields can also be extruded in the Z direction. This generates an Isovist surface, where the height of the surface is proportional to the value. This can help to highlight certain patterns.